right, hello everybody. I'm Simon. Today I'm going to talk to you about evolution of prediction serving system. So I work on prediction serving system, and I'm advised by Ian Stoica and Joseph Gonzalez. And for this session, we're going to do it a little bit differently. So I'll do the talk, and then I'll do an interesting demo. And then we're not going to have any tutorial because it has been a long day, and we believe you should sit back and enjoy. So after I'm done with my demo, I'm going to ask Rehan, my colleague, to come up, and then he'll also introduce another interesting piece of our prediction serving work at the lab. All right, and today I'm presenting work of many people. I want to thank them, and without them, this project cannot be successful. Now, all right, let's move on to prediction serving. Let's take a step back and think about the big picture. In our machine learning lifecycle, we have model development. That's where the data scientists gather data, analyze the data, and visualize the data. We have model training, which is you have play with in RayTune, for example, today, where you continuously train different models. And finally, we have the inference stage. Today, we're going to focus on the inference stage. This is where we want to serve many prediction service and then enable end user application to query these service, and then for our service to return prediction. Our goal is to serve prediction for large-scale interactive application. So in this session, we're going to introduce three systems. So Clipper is a low-latency model-serving system. It can serve any framework. And RayServe is a flexible pipeline-serving library that comes with a unique concept called traffic policy. And then lastly, Rehan will introduce you model Zoo.live, which is something we have been working on for quite a long time, and it's a model hub UI for discovery and management. And by the end of the talk, you should have some sort of picture about how these three systems fit together. In particular, Clipper is a low latency serving system and containerization engine that wrap any machine learning framework. And RayServe is a flexible control plane and data plane that scale to any number of nodes. And on top of that, we have model Zoo.live, which is a UI and management service for model sharing and discovery. An end user can send query to any of part of the components. Let me start by talking about Clipper and RayServe, and then I'm going to do a demo. So Clipper is a low latency model serving system. What the problem we're really trying to address at the time when we're developing Clipper is that there are a wide range of application and frameworks, and there is all these M times N problem with matching application for different framework. Clipper interposes between application and the actual machine learning model implemented in many different machine learning framework. And the design of Clipper is such that we act as middle layer that's for application, we serve RPC and REST, we expose a RPC and REST interface. And then for model, we expose an ultra low latency RPC system. So any application can talk to any models. There are a lot of interesting features of Clipper. So Clipper is container or cloud native. So you can deploy your model in a container and use any framework you like. And as well as, because we have container, we use a native versioning method with Docker container. This enables reproducible model deployment. We also have seamless replica scaling in Clipper, as well as built-in metric monitoring that's exporting Prometheus metric, and it is ready for Kubernetes. And additionally, Clipper integrates with interesting research has done in this lab, where we study interesting advanced batching algorithms such that we can achieve high throughput with low latency. This enables us to use expensive hardware like GPU to serve our models. However, in this talk, I want to mainly address some limitation we found using Clipper, developing Clipper, and deploying Clipper in production. One of the limitations is the scalability of Clipper. Clipper, the system as a whole, it has two parts. It has a multiplexer which routes query from HTTP endpoint to different model containers. And when the query starts to getting a lot of, when we start to get more traffic, and Clipper is able to scale the model one by one, adding more replicas. However, Clipper multiplexer itself only runs on a single machine, even though all these models can run on a separate machine. But when the traffic is so high that the multiplexer is using all the resource, Clipper just stops scaling anymore. This is a time when we have to serve higher number of throughputs, we have to manually add an additional Clipper. But this requires user to add the Clipper instance and then put it on the separate nodes and then manage different models to put it behind the second Clipper multiplexer. Clipper has very limited scaling. Clipper multiplexer does not just scale beyond a single machine. Now I want to talk about the second limitation of Clipper. That is, Clipper is built for a single model. This dot right there is a single model. But what we found out in actual production, model actually work inside a pipeline. These pipelines are composed by many different models. For example, you have featureization first, and then you put it to a downstream model. This pipeline can take many forms, including ensemble, cascade, and different split-ish policy where you have A/B testing, selection policy, or even just split among different versions of the model. And let's take a deeper dive of how we can handle pipeline really just in the current Clipper framework. So say we have a pre-processed model pipeline that has model A, and that sends request to model B. Well, as a client, we have to send the query to Clipper, get the result back, that's the intermediate result, and then send the intermediate result to Clipper again to get the final prediction back. However, as you can see, there might be some issue here. The two queries in the middle, they're just wasted bandwidth. That's network requests that should never be there, and we have missed a lot of interesting optimization opportunity. Clipper has no native support for pipeline, even though pipeline are common. And we have missed a lot of interesting pipeline composition and missed a lot of optimization opportunity. And let me point out here, we believe this issue is not just belong to Clipper, like system like TensorFlow Serving or Microsoft Onyx Runtime also has this kind of problem of it is not aware of multi-model composition and not aware of upstream and downstream model, they only serve one single model. Lastly, let me just briefly mention one more limitation of Clipper, that is the high data transfer cost. Say the client wants to send an image for prediction, this cat image, to a model. So the client will first send the image to Clipper, and then Clipper will send the same image using the network to the model. What does this mean is that even though Clipper and the model can be on a single node, we're duplicating this network request, and this incur high data transfer costs, especially when we're under high load. Now, can we really address this issue with Clipper? Where Clipper has limited scaling, it doesn't have native support for pipeline, as well as a very high data transfer cost. Let me introduce you to Reserve. So what we're aiming at for Reserve to do is flexible pipeline serving with traffic policy. Reserve is supposed to be a serving system that can scale to any scale. And let's take a step back. In Clipper, this is the picture you just saw. But in Reserve, building on top of Reserve can scale to many number of nodes and can dynamically scale up and down. This is benefited from Ray's design, its bottom-up scheduling, and its flexible sort of fault tolerance mechanism. And in Reserve will act as a central control plane and data plane spanning multiple nodes. And then we'll talk to you, for example, Clipper model containers, as well as we can even talk to TensorFlow serving containers, or even Onyx Runtime, or any prediction serving system that serve a single model. So this, with Ray, we really address the limited scaling limitation of Clipper. Now let me talk about how do we support pipeline. Well, how do you support pipeline? We just build the pipeline as a core concept into Reserve. If we want, let's get back to this upstream, downstream pre-process pipeline one more time. In Clipper, the client will send the request to Clipper, Clipper will send it to A, come back, and then the client will get the intermediate results. The client will send the request again to Clipper, and finally, the final result will come back. In Reserve, because of Reserve is aware of the pipeline, when A returns the intermediate result to reserve, reserve will be able to directly send the request directly to B, and we get the result back. The client never sees the intermediate result. The redundant network request never happens. Now, this is how reserve addresses native support for pipeline. Lastly, let me quickly talk about how does reserve handle the data transfer cost. Let's say if a client wants to send request to reserve, in this current system now, in reserve now, we have a new component. That is Apache Arrow Plasma Store. Plasma Store is an in-memory object store inside Ray, which is something you have played with today. The client will just need to use a single ray.put to put the object into Plasma Store, and then just pass the object ID, the reference along to reserve. The reserve will pass the reference to the model, and the model, when the model is reading that object, because of Plasma Store, the model can use zero copy read to directly read the object. This is how we reduced high data transfer cost. Well, what else does reserve bring to the table? So other than addressing Clipper's limitation, reserve also has a concept of endpoints and backends. Let me briefly explain them. An endpoint is a single URL route endpoint that can be invoked from HTTP, as well as a Python invocable endpoint. What does this mean is that you can send a request to an endpoint through HTTP using JSON request or whatever, as well as send the request directly in Python. This is a critical component for pipeline serving. And an endpoint can send traffic to any number of backends. A backend, you can think of them as replicated model actors. Some of you might know these as identityless actor pool. So these backends can scale up and down individually, and they can be spanned among different number of nodes. Now, this kind of two-level of abstraction enable a new concept in reserve. That is what we call traffic policy. Traffic policy enable flexible traffic shaping. So in this picture right here, the endpoint can send 80% of traffic to backend 1 and 20% of traffic to backend B. So, and this kind of simple split architecture can enable us to perform advanced functionality like routing upgrade. And then if you find out some model version was wrong or there's a bug in them, you can immediately roll back the traffic so users are not affected. You can perform interesting patterns like A/B testing or even advanced selection policy. Now, one last thing I want to address is that are we just going to leave Clipper behind? No. Clipper is still great for single model serving, and in addition to that, reserve will implement all the features in Clipper as well. This includes batching, latency awareness, seamless replica scaling, and more importantly, reserve will be able to talk to any Clipper containers. So rather than telling you more about this, let's dive into reserve. I'll start a demo. So right now, I'm in a Jupyter notebook. Our scenario is that a data scientist deploying a topic classification model. So the topic classification model functions like the following. You're taking any string, any English sentence, and then you'll classify the sentence into 4 topics right now. So we'll say, is this sentence related to graphics card? Is this sentence related to the Windows operating system? Is the sentence related to Mac or even just aerospace? So for example, I like MacBook will be classified into the things about the Mac hardware, and then GPU expensive will be classified into comps.graphics. So this is actually a pretty common problem in industry. If you think about how would this kind of classification model can be applied to classifying product review on Amazon, classifying customer feedback or complaints on Twitter, or even just classifying basic user support emails. And Ray is currently an experimental library under Ray, and then we'll initialize Ray just like how you learned today, use ray.init. When you start serve, Ray serve actually starts with multiple components right here. We have a routing table, a queuing system, and HTTP server. I'll explain them a little bit. But however, on a multi-node machine, you will run Ray up, as Philip has shown in the morning today, and array server will be able to connect to the existing system. So after you run serve.init, we start as 3 components. We start an HTTP server, listening to some port. We start a router actor, and we start a persistent key. We have something talk to a persistent key value store. And in the multi-node setting, all the HTTP server, or the queues, or what we call routers, are all array actors. And we can also directly serve model inside array using any function or object, or we can instantiate them as array actors as well. On top of that, we can talk to any container, including Clipper container or for serving container, using a shim wrapper of array actor wrapping those containers. And with the capability array, we can scale to many number of nodes, and the configuration data is stored in a persistent key value store. So you can always, even though the cluster crashes, restoration can be always done automatically. Now, let's first create an endpoint called classify in our system. So as you can see, for endpoint, we also associate a HTTP route with the endpoint. So this will enable user to ping HTTP request to /topic/classify. Now, what happened here after we created endpoint is just a new entry in the routing table, in the URL table. So the HTTP server now knows to match /topic/classify into what we call an endpoint called classify. I'll explain what's the point of the endpoint immediately after. Now, let's create our very first model. I would say, as a data scientist, I wouldn't try so hard to use deep learning for our first iteration. So let's use a very simple if-else statement to classify our basic sentences. As you know here, we actually, because we serve as a capability of serving requests both from HTTP as well as from Python, we need to handle how do we handle the mismatch between HTTP request is in the HTTP encoding and the Python requests are just native Python function calls. So when you're implementing a reserve callable object, we ask you to take into a Flask request. Python's Flask framework is a very powerful framework that allows you to build web application very easily and is very popular among especially data scientists. And the Python request, if the function is invoked from Python, the input string argument, keyword argument will be used. And the user can use serve.context.web to distinguish whether we're serving requests from Python or from HTTP. And while we're returning just a simple JSON serializable object for now, let's create this backend. My bad. We haven't run this in this cell. And let's create this backend. And what happened now is a new actor has started in the array system. And this actor knows to fetch from the router using the tag topic v1. However, the HTTP server is in queuing request to the classify queue. We don't have any connection between the topic and the topic v1 right now. So one more step right here is serve that link. With serve that link, the router will be able to know that for any request coming in to classify topic, we will send 100% of the traffic directly to the topic v1 backend. All right, let's try to ping the service. Hopefully this is gonna work, and then we'll get a JSON back. Right now, we see that if we send a message, map is great. We get a classification of it belongs to Mac hardware, and the models are just basic if-else statement. And another feature of reserve, as I just said, is that not only you can ping it from HTTP, but also you can directly call it from Python. We'll use serve.getHandle. This is a handle object in reserve. When you call .remote, using under the handle with a keyword argument, you get an object ID back. An object ID is this object ID is just simple array object ID. What does that mean? You can use simple array.get to retrieve the result. And it's also pretty princess, so we know if we just do MacBook, the output is unknown because our if-else classification model is not that good. Well, and now this is good, but we see that if we just send a very simple sentence like mapbook, the output is unknown. Let's deploy a brand new version using scikit-learn. This is the power of machine learning. Let's test it out. However, we're gonna make it a little bit challenging. We're going to deploy a fancy model here where we get the pipeline and classification details. And then, however, we're gonna use a buggy version of our model. We're gonna have some bug in your code and see how will reserve handle that. Let's instantiate this model, let's create a new backend, and then let's try to retrieve the handle. So what happened immediately now is that a new actor is created, just like before. However, even though the new actor is fetching from the router saying, hey, I'm topic v2, please send query to me, the router are not going to send query to topic v2. And this is because right now the router is configured to send 100% of traffic directly to topic v1. Now, we'll use a new API called serve.split to split the traffic between topic v1 and topic v2, and then the handle will also show the corresponding traffic policy. What happened now is that the router is aware to send the traffic 50-50, and then each traffic is evenly split. Now, let's send some queries. Okay, the first one comes back. Let me send one more time. So we see some error that comes from the second model, while part of our queries also return with the correct response from the very basic V1 model. And right here we see, so for example, these results are from our version 1 that's still working, while these errors come from version 2 that somehow has some internal issue we need to figure out what's going on. Now if we're serving this for production, this is bad. Let's first roll back our decision. Let's have 100% of the traffic send it to the V1 model while we have time to debug and figure out what's going on with V2. So we'll create a new endpoint for debug, and then we'll get a handle, and then directly use a debug handle that remote with the input string. So right here, when we call rate.get on the object ID return, we actually get the original error back with rate task error, and then we see that type error, only integer, blah, blah, blah. This is a familiar error common in scikit-learn, and the data scientist will commonly know what's going on there. So now so our V1 is working, V2 is buggy. Let's actually deploy a fixed version of our V3 that works. I'll do so by uncommenting the line, and then let's deploy the brand new model, and then set the traffic policy to 50-50 again, and then when we query the model, we can get scikit-learn result back as well as from the if-else statement from the V1. And when the request, when we figure out the advanced V3 model has been good enough, after we evaluate this metric, seeing that that's actually increasing customer success, we can actually call serve.split one more time to shift all the traffic to topic V3. Now, there are also a lot of additional features Racer brings to the table, well, including serve.scale API that can scale any backend to any number of replica using the power of array. And serve.stat will return the metric. And lastly, let me tell you how we're making Racer pipeline native. So the pipeline can just be any Python function again. You can take in the Flask request or any keyword argument to enable it to be invoked directly from Python. And then we'll just get the handle like we did, and then use .remote to sort of get the result from for example, right here is the topic of AI version, and then we can pass it along to the intermediate result directly to the subsequent model, and finally return the result directly back to the user. So intermediate result never goes back to the user. Well, now that's my demo. I'll introduce Rehan to the stage, and Rehan is going to show you another interesting system we're building that might surprise you. That's not the common prediction serving system.
the mic real quick.
Yeah, any questions so far? Yes, good. Right, yes. Yes. So the question was about arrays designed for training and inference as well. And Clipper is designed for inference only. With reserve, in fact, we are not constrained to just inference, as you might think. But however, we can also support maybe interesting online learning use cases. And like there's not, reserve object can also just have states. It can be any object. We can even just train a machine learning model on the fly. Yeah. Yes. Mm-hmm. Right, so we will rely on Ray to span across the cluster. And however, we'll use some interesting feature of Ray to associate our actor or object on different nodes using Ray's concept of dynamic resource. So reserve itself does not have a concept of a cluster. Yeah, cool. All right, so welcome, Rehan.